In today's video, we will look at inelastic collisions and explosions. In inelastic collisions, kinetic energy is not conserved, and some of that energy is lost in the form of heat or deformation energy. However, if the colliding objects form an isolated system, their total momentum is always conserved. So, unlike elastic collisions, where both momentum and kinetic energy are conserved, for inelastic collisions, only the total momentum is conserved. So we see that the common point is no matter what kind of collision you're dealing with, momentum will be conserved if the colliding objects form an isolated system. So we have that P total initial is equal to P total final. And so M1V1 initial plus M2V2 initial is equal to M1V1 final plus M2V2 final. And if the two objects stick together and move as one after the collision, then we say that the collision is perfectly inelastic. Here's an example. Read through the problem and then we'll solve it. We will now solve the problem. We know that since the total momentum is conserved, M1V1 initial plus M2V2 initial is equal to M1V1 final plus M2V2 final. However, remember that we are dealing with momentum vectors, and so all these velocities are vectors as well. So we add the little vector symbols on top to remind ourselves of that. Now let's plug in the values. Plugging in, we see that for case 1, M1 is 5 kilograms, V1 initial is 3 I hat, M2 is 10 kilograms, V2 initial is 2 I hat, and in this case we don't know what V1 final is, but we know that V2 final is 2.5 meters per second I hat. Alright, simplifying, we get 35 Newton seconds I hat on the left hand side, sorry, and this term simplifies to 25 Newton seconds I hat. So solving for V1 final, we see that V1 final in the first case is 2 meters per second I hat. So the 5 kilogram block continues on to the right at 2 meters per second, a slower speed. Following a similar procedure for the second case, the left-hand side is still the same, but now the 10 kilogram block has a velocity of 4 meters per second to the right. The left-hand side simplifies to 35 Newton seconds I hat, and now the second term on the right-hand side is 40 Newton seconds I hat. Solving for V1 final, we see that V1 final is negative 1 meters per second I hat. In other words, the 5 kilogram block now bounces back to the left at a speed of 1 meters per second. Now, if we were to look at the kinetic energy before and after in these cases, sometimes we would find that the kinetic energy had decreased, sometimes we would find that the kinetic energy had increased. If it decreased, the reason would be because some of the kinetic energy was converted into heat and sound and deformations. If it increased, that means there must have been an explosion or a release of energy at the moment of impact, and that is what contributed to the extra kinetic energy. Here is another problem. Read through it and try and solve it yourself. Let me note that you will need both a knowledge of momentum conservation to deal with the collision, and either kinematics or energy conservation to find the maximum height. We will now discuss the problem. Initially, the block is not moving, but the bullet is, and so all the momentum of the bullet block system is contained in the bullet. So we see that the total momentum initially is just the mass of the bullet times its initial velocity. So here I'm denoting the bullet as m1 and the block as m2. Plugging in the numbers, we get that the initial total momentum is 10 kilograms meters per second j hat. Don't forget to convert the 10 grams into kilograms. In the final situation, both the bullet and the block are moving, and since the bullet has emerged from the block, they are not moving with the same velocity. So we have P final total is P1 final plus P2 final. We can calculate P1 final since the bullet is still a 10-gram bullet and now the velocity is 400 meters per second. But we don't know the velocity of the block. Still, simplifying, we get P final is equal to 4 kilograms meters per second j hat plus P2 final. Since the total initial momentum should be equal to the total final momentum, we can say that the final momentum of the block is 6 kilograms meters per second j hat. Now, knowing that the block has a mass of 10 kilograms, we can use that to find the velocity of the block. And so what we find is that the velocity of the block just after the bullet has passed through it is 0.6 meters per second j hat. However, the question doesn't end here. We are asked to what maximum height does the block then rise above its initial position. So now we have the initial velocity of the block. It's 0.6 meters per second j hat. And we know it's moving up in the y direction, and that the only force acting on it once the bullet has left is the force of gravity. So we could use either kinematics or energy conservation to figure out the maximum height to which the block will rise. I will use energy conservation. So we have the initial total energy should be equal to the final total energy. K initial plus U initial is equal to K final plus U final. However, now we are looking at the situation after the bullet has left the block and the block is rising up by itself. So what we call the initial and what we call the final has changed. The initial is when the block is here and the bullet has just finished passing through. The block has picked up some velocity, but it hasn't yet started to rise. The final situation will be when the block has risen to its maximum height. At that point, its vertical velocity would be 0, because that is the maximum height. If it wasn't 0, then the block would keep on moving upward. So, understand and note that the initial and final situations that we're dealing with have changed. The initial is just after the collision now, and the final is at the maximum height of the block. So, we know the initial velocity is 0.6 meters per second, and we can take the initial height to be 0. We know that the final velocity is 0 meters per second since it has reached the maximum height, and we have an unknown height that we need for the U final. Plugging in our expressions, we have 1/2 mv initial squared is equal to mgh. Solving for h, we have h is equal to v initial squared over 2g. We know that v initial is 0.6 meters per second. We can take g to be 10 meters per second squared, and so we find that the final maximum height to which the block rises is 0.018 meters. In other words, 1.8 centimeters. Not very high, but that's because the block is so massive. Let's move on to the next slide. So, now let us consider explosions. If we consider an isolated object that explodes, its momentum is conserved. The simple way to see this is to think of an explosion as being a perfectly inelastic collision run in reverse. Here, the objects start out stuck together and then move apart in the reverse of a collision. The kinetic energy of the particles after is clearly not the same as the kinetic energy before, and this extra energy comes from the stored chemical energy or spring potential energy that the original object had. Again, notice how, just like with the usual inelastic collisions, momentum is conserved, but kinetic energy is not. Here's a sample problem. Try solving it yourself first, and then we'll look at the solution. We will now solve the problem. The initial situation is a 4 kilogram box sliding across a frictionless floor with some unknown velocity. It then explodes into two pieces, a 1 kilogram piece moving north at 3 meters per second and a 3 kilogram piece moving 30 degrees north of east at 5 meters per second. Let us set up the momentum conservation equation. I will denote the 4 kilogram mass as capital M, the 1 kilogram mass as MA, the 3 kilogram mass as MB. We've set up the equation, but again remember, the velocities are vectors, so we need to write these velocities as vectors in unit vector notation. We will set up the usual coordinate system, where north is in the positive y direction and east is in the positive x direction. Using this coordinate system, we see that the velocity of piece A is 3 meters per second j hat, since it is sliding due north. And similarly, the velocity of piece B is 5 cosine 30 degrees meters per second I hat, plus 5 sine 30 degrees meters per second j hat. What we have done is taken the 5 meters per second speed and 13 degrees north of east direction and converted them into components. Plugging all this into our original momentum conservation equation, on the left hand side we have 4 times v initial, MAVA becomes 1 times 3 j hat, and MBVB becomes 3 times 4.33 I hat plus 2.5 j hat. Simplifying, we have that v initial is 3.25 meters per second I hat plus 2.625 meters per second j hat. We are asked for the original speed, so now we can take the magnitude of this velocity, and that will be our answer. Notice how all we used was momentum conservation, and keeping in mind that velocity and momentum are both vectors. Here is another problem. Try and solve it by yourself. Keep in mind that some of the speeds are given relative to Earth and some are given relative to the command module, and it's best to do all the calculations relative to the Earth. Using that and momentum conservation, try and solve this question. Pause the video while you try. We will now discuss the answer. We will introduce some notation. We already have that the command module has a mass m and the rocket motor has a mass 4m. Let us call the 4,300 kilometers per hour that the space vehicle initially has relative to Earth as v initial. For simplicity, we assume that the vehicle is traveling in the positive I hat direction. Next, let us call the velocity of the command module relative to the Earth after the separation as vc final. But to be clearer, since we will be dealing with relative velocities here, we will write it as v of the command module with respect to Earth final. We are also told about a speed of 80 kilometers per hour. This is when the rocket motor is sent backward with a speed of 80 kilometers per hour relative to the command module. How should we denote this? We say that this is the velocity of the rocket with respect to the command module, and that it is negative 80 kilometers per hour I hat, since it is being sent backwards. Now, to apply momentum conservation, we need all our velocities to be with reference to the same observer. In this case, the easiest choice is to have all our velocities to be relative to Earth. So, we need to convert this velocity of the rocket with respect to the command module into a velocity of the rocket with respect to Earth. Let's use our usual relative velocity equations to see what the relationship is. We start the usual way. We write the easy stuff first. Since r is on top over here, r must be on top over here. Since e is in the bottom over here, e should be on the bottom over here. And our three objects are, of course, the rocket, the Earth, and the command module. So C fills in the middle spaces. Filling in what we know, we realize that this term is what we had just found out, the negative 80 kilometers per hour, and this term is the velocity of the command module with respect to the Earth. And since we are looking after the explosion, this is exactly what we previously called VCF. And so we have negative 80 I hat plus VCF. Now we are ready to put all our information together. The initial total momentum of the space vehicle is equal to the final total momentum of the rocket plus the command module. Plugging in the values, we know that initially the two masses are combined, so we have 5m here times the initial velocity, and then we have 4m times the velocity of the rocket with respect to the Earth, plus m times the velocity of the command module with respect to the Earth. Further plugging in the expressions we derived and the numbers that we know, we have 5m times 4300 I hat is equal to 4m times negative 80 I hat plus VCF plus m times VCF. Simplifying all this, we have 21,820 I hat is equal to 5 times VC final. Notice I have cancelled out the m's. We can further solve this to get the final velocity of the command module with respect to the Earth in units of kilometers per hour. And that's the end of that problem. Here is our final problem for this video. Again, read through it yourself, pause the video while you try and solve it, and then we will continue on with the answer. We shall now discuss the answer. We notice that initially the system of the two particles in the spring is at rest, so the initial total momentum is 0. And since that must be equal to the final total momentum, we have that PA plus PB should be equal to 0. We also know that the mass of A is twice the mass of B. We also know that the initial potential energy is 120 joules, and that it is all converted into kinetic energy. And so we have that Ka plus Kb should be 120 joules. Since this problem involves both kinetic energy and momentum, it is useful to look at the relationship between them. Before we go on with that though, let me add one more piece of information. as you can see, we currently have four unknowns, which are PA, PB, MA, and MB. KA and KB can be expressed in terms of PA, PB, MA, and MB. So we have four unknowns, but we only have three equations. This is clearly not enough to completely solve the problem, so let's add one more piece of information to the problem, which I neglected to add earlier. The extra piece of information that we need is that the mass of A plus the mass of B is 30 kilograms. Now we have four unknowns and four equations, and we can solve the problem. So now let us proceed on to the relationship between momentum and kinetic energy. We have seen in class that kinetic energy, which we usually write as 1/2 mv squared, can also be written as p squared over 2m. Using this expression, we can say Ka plus Kb is equal to Pa squared over 2Ma plus Pb squared over 2Mb, which should be equal to 120 joules. However, we also know that Pa plus Pb is equal to 0, and so Pa squared should be equal to Pb squared. Further, we know that Ma is 2 times Mb. So, rewriting our expression, we have Pb squared over 4Mb plus Pb squared over 2Mb is equal to 120, where I have substituted Pb squared instead of Pa squared and 2Mb instead of Ma. Adding these two fractions together, we get 3Pb squared over 4Mb is equal to 120 joules. Solving this, we have Pb squared is equal to 160 times Mb. Now to go further, we need to use that last piece of information, which was that the total mass, Ma plus Mb, was 30 kilograms. Using that piece of information, along with the fact that the mass of A is 2 times the mass of B, we find that the mass of B is 10 kilograms. Plugging this in, we have that Pb squared is equal to 1600, or in other words, Pb is equal to 40 Newton seconds. That is the magnitude of the momentum of B. Thus, Pa would also have the same magnitude. And so, putting all this together, we have MAVA, which is Pa, is equal to 40 Newton seconds, is equal to MBVB. We already know that the mass of B is 10 kilograms, and so we have that the speed of B is 4 meters per second, and since MA is 20 kilograms, the speed of A is 2 meters per second. That is the end of this problem and this video. I'll see you in the next.